Hello, welcome everyone to the first webinar in D2K's Machine Learning webinar series, Decision Trees, Deriving Decisions Logic from Data. My name is Maria Walker, CEO of D2K Technologies, and we thank you for taking this time away from your busy schedule. I'd like now to introduce our Chief Technologist to lead us through the webinar, Mark.
Thank you, Maria, and welcome to D2K's first machine learning webinar. Decision trees, deriving decision logic from data. Well, you may be wondering, why decision trees and why machine learning? For D2K and our customers, it's all about extracting information and knowledge from data. That's knowledge that can be expeditiously be used in software to increase availability in production, to improve product quality, to assure safety and environmental protections, to extend the life of process equipment, or even to guide and control systems and subsystems autonomously. The D2K engineering team has been working with NASA and other intelligent systems practitioners from industry to research, to develop, to test, and to validate machine learning algorithms for many different purposes. Some of those include increasing situational awareness, performing root cause analysis, predicting future anomalies and the need for condition-based maintenance, autonomously managing manned and unmanned mission-critical systems. So a lot of these machine learning techniques, they're focused on categorizing, on classifying, on trending, correlating, estimating, predicting variables in process health and process performance in order to make informed and actionable decisions. So it's really all about the decisions. But in terms of applying machine learning algorithms to solving problems, how do you even begin to choose which machine learning algorithm paradigm to employ? Let's take a brief look at the spectrum of big data analytics, and specifically at the artificial intelligence and paradigms associated with machine learning. These include both supervised and unsupervised learning paradigms, employing statistical and Bayesian approaches, distance-based clustering, support vector machines, Kalman filtering, decision trees, genetic algorithms, and biologically inspired deep learning techniques using a variety of artificial neural networks. As it turns out, many of these techniques are actually useful for solving the same kinds of problems, particularly for classification of input data or the creation of decision boundaries among input data patterns. Let's take a look at a flatter look at this universe of big data analytics. Notice that decision trees, even within the realm of decision trees, there's actually many different algorithms that can be employed. We're not going to actually categorize or distinguish much between these different algorithms, but we'll spend a little bit of time talking about each one of them. What we want to focus on is the utility of inferring decision trees and decision boundaries from data using decision trees. So let's just take a look at what is a decision boundary. In this particular simple case, we've got two dimensions. We've got two parameters, one on the x and one on the y axis. And you can see in this case that you've got some cluster of class in blue and another cluster of class in red. And if in fact you can define a decision boundary, such as this diagonal line that's shown in the picture, you can in fact completely separate these two classes, distinguish them and classify them when given a new pattern. And I want you to consider also that these classes may in fact represent control decisions. So the blue may represent a kind of control decision or a specific control decision. The red, a different control decision, and the decision boundary basically is what is defining how a particular decision to make one control decision is made versus another control decision. As a kind of a simple example, let me give you a simple data set. In this particular data set, actually, it's baseball season. So in this particular data set, what we've done is we've documented when we've actually chosen to play baseball, and we've documented a number of parameters like weather parameters, like temperature, like humidity, like wind. And then we've documented based on whatever decision-making process that we follow or that we employ, we've documented whether or not we played. If you apply the decision rule approach to this data set, what you get is what you might expect. You get a decision tree that actually represents and characterizes the decisions based, in this case, upon categorized inputs. When it's rainy and strong wind, we don't play. If it's sunny and normal humidity, we do play. So let's take a look at what is a decision tree. The decision tree is a tree structure containing decision nodes. Those are the nodes that indicate the feature that will be tested. So for example, a parameter, inlet temperature, or something like that. The branches themselves, they represent the possible values for the attributes, and so this can very often be captured symbolically. Rising temperature, rapidly increasing pressure above some specific numerically valued threshold. And then you've got the leaf nodes themselves, the terminal nodes. Those represent the final decisions along a particular branch. So this is just a presentation of some of the most popularly used algorithms for decision tree building. The ID3, the CART, and the C4, 5, and 5.0 algorithms. We've listed these here based on some of their strengths and weaknesses. And in particular, we've kind of zeroed in on and are using the C4, 5 algorithm in our own development because it allows us to use both symbolic and continuously valued numerical inputs. It allows for multi-way splitting, and it's based on an entropy measure. Everything that we're going to actually demonstrate today actually is using software that we've built. It's a platform that we use called Be Aware, but basically what it allows us to do is rapidly implement various different machine learning paradigms, employ them, test them, validate them. So the way that the actual decision tree is built is it's done using a top-down approach where we recursively split the data by identifying the attribute and the splitting criteria that give the best homogeneous sets. Splitting then stops when all the samples in the data set have some target value, or basically we've created a pure data set. So we mentioned entropy. Essentially, the idea here is that we want to capture or characterize the extent that the data set itself is separable, right? And so it's essentially a sum operation over all of the input data patterns, and it follows this particular formula. And essentially, a very high entropy would characterize impurity, whereas a low entropy would give us a data set that's actually very pure. So it's a measure of how separable the data set is. And the recursive action that we described a minute ago of the algorithm actually is based on determining where the optimal split points are located. And these are done basically by the algorithms calculating the information gain for a particular candidate split. And so the information gain is calculated by the difference of the entropy of the parent node with the average entropy of all of the children that are produced by that particular split. And so the objective is to essentially measure and then choose the split point that provides us with the most information gain. Let's just talk briefly, just for a second, a little bit more about decision boundaries. Imagine two clusters that are in fact concentric. The challenge here would be, all right, how can in fact a decision tree approach be used to actually isolate and separate these two different classes so that in fact we can derive the right reasons for why decisions were made? For this next part of the demo, I'm going to actually use some of the software that we've developed that's implemented the C4-5 algorithm. And in particular, I'm going to use a utility here to help illustrate this whole notion of decision boundary creation and splitting of the algorithm. To do that, this particular tool allows me in 2 dimensions to actually create any number of categories or classifications. So for example, if I start here and I start creating a scatter plot of input data of a particular category as identified by the color, and then I come along and I create another class, you can see that right away the software will immediately find a split, create a tree, and show us in fact how these particular patterns can be separable. If I get a little more complicated, you'll see that in fact the algorithm will find multiple splits, and as we go into multiple categories, you'll see that the algorithm will find as many splits as it needs to properly separate the data set. Notice that the tree, as I require more and more split points, the tree gets deeper. If we were going to be evaluating more than just an X and a Y input variable here, we would actually create trees that were broader and wider as there are more features to evaluate. But the idea is that we can actually do this and create relatively complex test cases where the algorithm is expected to appropriately and successfully separate the classes using decision boundaries, which will create a pure data set. Going back to an example that I alluded to earlier, I want to show you that, in fact, we can handle the nonlinear classification problems, and it becomes a relatively simple set of split points where we can take concentric circle classes and create decision boundaries, make that clear. But now what I'd like to do is actually like to show you how we actually employ the decision trees in software operationally. Not only can the decision trees be generated from data, we can use those decision trees once they've been blessed to actually provide recommendation to operators, guidance to operators. But we can also actually take that decision tree and turn it into a controller, and we'll show that in our next example. So this part of the demo, what we're going to do is we're going to actually use some real software where we've implemented a decision tree algorithm that can be applied to data. And what we wanted to do in this particular case is we wanted to create a system that would allow us to generate the data file that we could then feed into the decision tree algorithm, have it infer the decision tree, and then show how that same decision tree can be used to either provide guidance for operations or in fact be used in a real-time mode where it actually can act to interact with the control system. So what we've done is we've actually created here a simulated greenhouse environment. And we've also written the software here that will actually provide the simulation. It's a physics-based simulation so that we generate temperature cycles. And on this graph here you can see in the blue is the external temperature, and that's cycling about some normal daily cycle. And then with some insulation around the greenhouse and a couple of key control items, we then can maintain and control the internal temperature, which we like to keep at around some set point. And so it turns out that we've got an actual window or opening that can let out heat, but we also have an air conditioning and heating unit, which can either be turned on to heat or can be turned on to cool. And then there's a set point for comfort level. And the idea here is that we'll simulate the environment, but we'll also create a control system. And the idea is that we want a control system that will create a decision logic for controlling the temperature that is human understandable, so that we can actually use our intuition in validating the decision tree algorithm and also the performance of the control system when we're finished. So I will spare you the details on how we actually created the simulation, but suffice it to say that right now, with no action, I'm in manual mode, as you can see from this control mode, that the temperature internal to the greenhouse is just going to cycle as it's being impacted by the external temperature. All right, very quickly I'll mention that we've created a state diagram based control that basically allows us to create how we want this to behave, essentially our rules, if you will. They're graphical rules. This will govern the control system. We will then take that data, record that data, and then feed that data file back into the decision tree algorithm, and it will then produce the decision logic in tree form that should represent our control system, right? So this is what we will demonstrate here. First of all, notice that what I'll do here is I'll set it up so that it's being controlled actually by the state machines. And actually, if I were to show you the state machines, you'd actually see these animating as they're going from one state to the other. And what we would expect to see is that we'll get a tighter control about our specified set point. So let me change this to Fahrenheit because that's what I'm used to. So let's say we set this at around 70, and what we'll see is that based on that desired set point, the control system and these state diagrams will govern the control and manage the internal temperature of the greenhouse. I'm going to let that run for just a bit. I'll close these and I'll talk just for a second while that's running about the tree creation. So here we actually have the opportunity for importing the data file. When we're ready for this to execute, it will then generate the decision tree that is essentially being mapped from the data, in this case, the temperature, internal temperature, the state of the control system, the air conditioning in the window. So a few moments later, as you can see from my graph, my days are only a few minutes long. As you can see, the control system is actually doing exactly what it's supposed to do. You can see down here at the bottom of the graph, there's an indication of when particular control actions have been enacted and for how long. And so you can see there's both window controls and air conditioning, heating, and cooling controls. And throughout the cycle of a day, we're getting a nice, flatter, more around our desired comfort level temperature control. Now, all of that data then can be captured, as I mentioned earlier, in a file. We can then take that same historical data, maybe it's a year's worth of historical data, maybe it's a month's worth of historical data, whatever that might be. And then we can feed it through our decision tree algorithm building and then actually get out the resulting tree that follows from that logic. And so we can see that the control system behavior is actually being mapped and replicated in the form of this decision tree. Now, once we've inferred a decision tree, we can actually use that decision tree to provide advisement to the operators to perform the appropriate decisions at the right time. So we're going to select this now for by decision tree as advisor, and what we'll notice is that immediately we'll notice that the control of the temperature is going to now depend on operator action again, and so it'll start to deviate from hovering around our set point. But it's going to now provide, using our little message browser here, it'll provide the operator the guidance for actually performing the appropriate control decisions, the ones that have been blessed, the ones that have been verified after review of the underlying decision tree. So let's let this run for a while, and you'll notice that if I don't actually make the control decisions that are being suggested, the control system, of course, will fail to maintain the temperature. So here, for example, it's advising me to close the window, and now it wants me to start the cooling. It's getting too warm. And so the operator can obviously take action and try to keep up with the advisement of this decision tree. But the idea here is that we're showing that once the decision tree has been inferred from the data and then verified or blessed in terms of the control decisions being the appropriate control decisions and the basis for those control decisions being correct, we can then employ that same decision tree in a control strategy to provide the operator the advisement in terms of when to actually take the specific control decisions. So now what I'd like to do, though, is I'd like to actually do something a little more interesting, which is to take that same decision tree, incorporate it into the control system itself, and allow it to be the one that makes the decision as to what control actions to take. So in order to give you this example, I'll now switch to decision tree as controller. So just to be clear, what I'm doing now is I'm incorporating the actual decision tree to make the control decisions. I'm not using the state machine diagrams anymore, and I'm not using the operator's actions as advised. I'm actually using now the decision tree to make these decisions. And so what we would expect is that if we've done a good job of inferring the decision tree, we would expect that the control system now should behave very similarly to the way the control system behaved when being controlled by the state machine diagram. And as I let this run, you'll see, in fact, that that's the case. Notice that now our message browser actually is going to be providing us with information about what actions are actually being taken,
what actions were previously taken, and so on. And so if we watch this as it continues to run, we'll notice that when it's time, for example, to start cooling or to start heating, we'll see that the control system is actually being commanded by the decision tree to take those actions. And I can let this run for quite some time, and you'll be satisfied that the control system, as governed by the decision tree, is as good and quite similar to the control system that was actually being run by the explicit state machine diagrams. Just to review what we've shown here is that we can take data, historical data from some process where control decisions have been made based on some criteria. Maybe it's tribal knowledge, maybe it's actual control system logic and theory, just a feel for how the process is to be controlled. Take that historical data, push it into a decision tree inferencing algorithm, have it infer the corresponding basis for those decisions. That then decision tree can be examined, it can be validated, it can be pruned, which we'll talk about in a little bit. But once it's been validated, it is something that can in fact be deployed in a real operational environment and provide the basis for the guidance of a control system. So this is quite powerful, and it's something that we're leveraging now with a number of customers.
So I've already shown you the simple industrial example with the greenhouse and the temperature cycling and the ability to control, in fact, the temperature cycle using the decision tree. Now let's just wrap up the webinar with a couple of special considerations. First of all, what happens when there's conflicts in the data? If we've got multiple rows in the data set that have the same attribute value but different decisions, clearly that's a conflict. Decision tree doesn't know what to do with that. What you're going to end up getting is you're going to get some error where there's actually percentage of the time a certain decision made and another percentage of the time a different decision made, and that's reflected here as we can see this slide. Now, it turns out that this actually might represent an actual situation, or it could actually show you that you've got wrong decisions that are being made. All right, let's talk just for a second about overfitting. Overfitting is a problem whenever you're trying to learn any kind of a decision boundary. And it turns out that a fully generated tree can be perfectly accurate on the training data, but that doesn't mean it's going to perform well on unforeseen data, right? So the idea that we can train too much on too many fine details and overfit, or just have an incomplete data set and train and not have a good representation of the universe of possibilities. So overfitting is an issue with decision trees, just like it is with neural networks or other learning algorithms. But it turns out that there are ways that you can actually mend and address overfitting in decision trees. First of all, of course, you want to try to validate your data set. That means you want to take from the universe of samples a certain number of them that you're going to then use to help validate your algorithm. During validation, in fact, the tree can in fact be pruned, and so we'll talk a little bit about how pruning can actually be done. Turns out there's two kinds of pruning. There's pre-pruning and there's post-pruning. As it says on the slide here, pre-pruning is a user-defined stopping criteria. Now, that may be a nice way to manage keeping the processing time minimal. It also might be a nice way to manage keeping the tree to a manageable size. If you're going to introduce artificial stopping times, then you can be wrong, and you might in fact create erroneous trees. A better approach, of course, is to use post-pruning, and that is to prune the tree once it's built. And it turns out that post-pruning is a very interesting exercise in and of itself. And in fact, what we've done in our real-time systems is we've incorporated a certain post-pruning where the tree will in fact eliminate some of the branches and replace them with summary nodes. And the process goes like this. You build the decision tree, and then you remove the non-significant branches. Basically what you're doing is you're replacing twigs. Those are, as we've shown here, sections of a branch that have terminal nodes, where in fact I can take these two decisions and lump them into a single decision. And in some cases you might have an outlier where one of these decisions is a very small percentage of the time, and it doesn't make sense to make this distinction, and so on. And so what we've done is we've actually been able to automate the pruning process, and we can show that. Split the training data set into two subsets, the new training subset and the validation subset. Build the tree using the new training subset. Run the validation subset on the tree and measure the accuracy. Remove a twig at a time, run the validation set. Keep the tree that gives the highest accuracy on the validation set. Repeat steps 4 and 5 until there's no further improvement.
Okay, so now I'm going to go back into the software to give you a more thorough demonstration of auto pruning, and in particular we're going to focus on the validation process. So what we have here is we've got our system that's prepared to, in fact, infer from data and create a tree. We've got a data set that we've got already prepared that will essentially give us the information that we need to generate the tree, as we've shown you already. But what we've also done is we've gone to the trouble of extracting a certain percentage of that data set and setting that up for validation purposes. And the idea here is that the associations and correlations that exist in the data should be represented statistically in both sets. We're going to then use one set for training and use the other set for validation. And in our validation process, we've set it up so that it will auto prune the decision tree. So let me just give you a quick example of what I'm talking about. So here we're going to go ahead and execute this tree. You'll notice then that it's training, and then as it finishes, it creates the decision tree. Here's the decision tree that it's generated. And now what I want to do is I want to go ahead and validate this tree, but I also want to take advantage of what the validation process conveys or reveals with respect to parts of this tree which in fact can be pruned. So let me go ahead and do that. I'm going to go ahead and execute the validation. And if you take a look at the tree, you'll notice that in fact upon validation it has already performed the pruning action. Our decision tree is now improved. It's more compact. We haven't lost anything because the pruning process, as we explained, assures that the error is at least maintained, if not decreased. And so that's the auto pruning process.
So that completes our webinar today on decision trees. I hope that's been informative and you've been able to enjoy that. Now I'd like to pass it back over to Maria. Thank you.
Well, thank you, Mark. I hope you guys all enjoyed D2K first webinar. If you liked it, please don't forget to click the like button, and don't forget to follow us on social media, and stay tuned for our next webinar. Bye for now.